Hello, everybody. Let's talk about vectors. But before we do the notes, actually, let me like back up for a second. So vectors, a lot of you have said that you're in physics, and the way physicists often think about vectors is a vector is an arrow with a direction and a length. And you don't need to write this down right now. I'm just sort of like background, like who uses vectors for what. So again, those of you in physics, like a common use for vectors is if you need to add up a bunch of forces that are all like affecting an object. So like, let's say we've got an object and like something's pulling it this way, and the length of the arrow is the strength with which it's being pulled in that direction. So let's say it's being pulled that way by like a rope, and it's being pulled this way by gravity, and there's a giant fan that's like blowing it that way. So how do you combine all of those different forces acting at once? That's called a net force. And the way you do it is using vectors, which I'll show you in a second. It's vector addition. So you have a way of writing down like the x and the y direction for each of these arrows, and you kind of add them all up. So that's physics. And again, physicists think about a vector as just an arrow, a direction and a distance, a direction and a length, a direction and a magnitude. So let's talk about computer science. So if you're a computer scientist, we don't really think about vectors as arrows. We just think about them as lists of numbers. So two numbers. So it could be like 11,004. And each coordinate here represents a fact about something we're interested in here. So this could be like square footage for your house, and this is like number of bedrooms. And so you could have like a whole bunch of like data points. Like this is all the houses in Sunnyvale where you've listed what's their square footage and what's their number of bedrooms. And then you can do things. You could like plot them all in space. So if this is square foot and this is number of bedrooms, you could see like do houses, if you treat these as XY coordinates, do they form clusters? In computer science, usually we don't have vectors that are two-dimensional with just like two coordinates. Usually we have vectors that are many dimensional. So like Face ID, that like where you unlock your phone with your face, the way that it works is it finds important landmarks on your face, like edges of your eyes, center of your nose, edges of your mouth, and it records all of the distances between those landmarks. And so your face is represented as a single like 10-digit number. That's a vector. It's a 10-dimensional vector. And then like all the pictures of my face will cluster together in a 10-dimensional space, whereas like Neil's face will be over here because, uh-oh, Neil, you're in the video.
You have my consent.
Okay, all right, we got his consent. So we're hoping that like all of, like everybody's face like forms their own little cluster in the 10-dimensional space. And like if we're lucky later in the year, I made a whole bunch of stuff related to this, and maybe we could do it in our class. Okay, so physicists think about vectors as arrows. Computer scientists just think about them as lists of numbers, but typically in higher dimensional spaces. Let's just do the basics, which is like, let's think about rectangular and not rectangular forms, and then how do you do basic stuff like add vectors together and stretch and squish them and some other things like this. If you've done physics, this might be a review. All right, so vector tells you, let's think about it as a displacement or a motion. So the important thing about a displacement or a motion is it's like you're moving from somewhere to somewhere, but there's no particular place on the coordinate plane where a vector lives. So let's do one example. Usually you name your vectors with variables, but the thing that makes it a vector is this little like arrow with just one arrowhead on top of it. If I had two arrowheads, it would look like this. And you also see that sometimes in texts, but it's more common to just see V with like a little thing like that. And what you do is you write like what's the change in X and what's the change in Y between some triangle brackets like this. So we could say 2, 5, and if I wanted to represent that vector graphically, you could start it wherever you want, but the 2 just means let's go over 2 units, and the 5 just means let's go up 1, 2, 3, 4, 5 units. So this would be an example of the vector v. And like I said, it represents a motion. It represents I have moved this distance. Okay, we're back. But yeah, this one has 2 arrows, but really typically they just have 1 arrow. Okay, so that's the rectangular form of the vector. Rectangular means like in terms of horizontal and vertical components. There's also a polar form for vectors. So in our class, let's name it the same way. So we'll say A with a little arrowhead. But instead of saying like how far over, how far up, we'll give it a distance and an angle. So a distance of 4 at an angle of 30 degrees. So I'm only going to draw this kind of approximately, but 30 degrees, it's always relative to the horizontal. So 30 degrees is about that direction. But this distance is only about 1. And so, again, this is the distance, and this is the angle or the heading. So I would say, let's see, so like about there. So that's about the vector A, where we're assuming that this is a distance of 4. So it's just 2 different ways of thinking about a displacement. You could think about it as how far over, how far up, or you could think about it as point at a particular angle and walk a particular distance in that direction. I prefer radians at all times, but if you're going to use degrees, just include the degree symbol the way that I did. And I'll probably use degrees sometimes just if my purpose is to make the vector part be as understandable as possible to you. All right, so rectangular form, polar form. The magnitude of the vector is just a special name that tells you the vector's length. So depending on what form it is, this is either sort of easy or very easy. But first let's do notation. So these like 2 vertical bars, it looks like absolute value, but twice kind of. That's how you notate magnitude. So if I just write V, V isn't a number, V is a vector, it's 2 numbers. But if I write magnitude V, this really is a single number that gives you the length of the vector. Okay, so if I want to know the length of this vector, easiest thing to do is to think about it as the hypotenuse of this triangle. And like 80% of all math, it is the Pythagorean theorem. So I can just do 2 squared plus 5 squared. So it's 4 plus 25. Okay, in a second, I'm going to pause the video and you tell your neighbors, if I want to know the magnitude of this vector A, what would it be? All right, anonymous student, what is the magnitude of A?
It's literally just 4.
Literally just 4, because magnitude tells you the length of the vector, and in the polar form of the vector, that's just one of the 2 numbers. So yeah, just equal to 4. So always like think about what does it mean, and then either the information is given to you or you can solve for it. Okay, let's talk about adding vectors. This is like this fact I'm about to tell you is one of the main reasons vectors are so powerful. So let's say I've got a vector 2, 5 and another vector 3, -1. You can look at this picture and decide which is which. Let's see, this looks like 2, 5. So this would be vector A. And then this vector looks like I'm going over 3 and down 1. So that's the B vector. So visually, if you are adding 2 vectors, the way of thinking about it is, what if we perform the A motion first and then the B motion second? And then let's think, what's a motion that would get us to the same place in the end? So if I move along the A path first and then the B path, that would be the same as if I just moved along the dotted line, because it would take me to the same place in the end. It's the same displacement. So if I wanted to name that C, I could write this as C. So the big takeaway is adding vectors, you think about putting them end to end, but when you add them together, the result is also a vector that just starts at the very start of your path and ends at the very end of your path. Numerically, so that's graphically. Numerically, you just add up the components. So here if I've got the A vector is 2, 5, and the B vector is 3, -1, 2 plus 3 is 5. And you can think about it as separating out the X motion from the Y motion. So here I'm like go right by 2, then go right by another 3, and altogether I've gone right by 5. Here I'm going up by 5, go up by -1, which is like down by 1. And so then I'm left going up by 4. And so you can see the C vector goes over 5 and up 4, which is the result of adding the components. All right. You know, for numbers, it's true that a plus b should be the same thing as b plus a, but that's not necessarily true of other mathematical objects that you will encounter in the future. So it's worthwhile asking, like, are these two things really the same for vectors? So let's think about it both numerically and graphically. So graphically, we did a plus b. Here's what b plus a would look like. First, we move along the b vector, which is over 3 down 1. Then we move along the a vector, and the result is that dotted line. And you see the dotted line is the same, has the same components. It's still over 5 up 4. So it doesn't matter if we did the a motion and then the b motion, or the b motion and then the a motion. The net motion, the resultant motion, is the same in both cases. So that's a sort of visual case that it doesn't matter what order you add vectors in. Numerically, hopefully it's also pretty clear, but let's do it. So here's the b vector, here's the a vector, and again, if we're just adding the components, 3 and 2 is 5, negative 1 and 5 is 4, and so same. Okay, so scaling vectors. So that's if you're going to add two vectors. If you're going to scale a vector, that's like, let's take the vector and multiply it by a single number. And the number is usually called a scalar. Holy moly. All right, so let's just sketch a whole bunch of these. So let's imagine C, and then twice C, and 1.5 C, and negative C, and negative 2C. So C, let's sketch it, is over 3 up 2. Looks like this. Go ahead and sketch it. Okay, so 2C, this is scaling C by 2. So it's going to make it twice as long. And it scales both x and y by that same amount. So let's say twice as long, and then let's look at it graphically. So if it's twice as long, it's going to be over 1, 2, 3, 4, 5, 6, and up 1, 2, 3, 4. And like you could think about it as c plus c. You see how each of these c vectors happens once? Or you could think about it as the c vector just stretched to be twice as long. Either way would work. So this is twice the c vector. And then numerically, if you're going to scale your vector by a factor of 2, the c vector was 3, 2. So it's like just apply that to the x and y components separately. So the result would be 6, 4. And that's 2c. So as you might imagine, multiplying by 1.5 on the outside is just the same idea. It would be 1.5 times 3, 2, which would give us 4.5, 3. And it's like taking the c vector and stretching it to just be 1.5 times as long. 2, 3, 4. So here's 4.5. Here's 1, 2, 3. About there. So hopefully that's intuitive. It's like whatever number is there, it's just going to stretch your vector, same direction, different length. But let's think about what happens if it's negative. Good guesses. It just goes the other way. So this is the same thing as negative 1 times c. So numerically, that's just negative 3, negative 2. And that's the same as the c vector in the opposite direction. So here's negative c. And then negative 2c, it's like the c vector in the other direction, but also stretched twice as long. So that would be like negative 6, negative 4, and then we can sketch it here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Whoop. It helps to make that noise. All right, so just like following along there, let's sketch v plus w and v minus w real quick. So v is over 5 up 2. 1, 2, 3, 4, 5 up 2. Go ahead and sketch it. So that's v. And then w is negative 2 up 2. So this would be v plus w, that pink one, because it's the same resultant motion if I did v followed by w. V minus w. So remember, negative w is like the w motion, but in the opposite direction. So negative w would be right by 2, down by 2. And if I'm adding it to the end of v, it's like first I'll do the v motion, then I'll do the negative w motion. So see how it's like just like the w motion, except it's the opposite direction? That's how come negative w. And I drew it at the end of v because I want to do first v and then negative w. So here you see this is v plus w, this is v minus w. Convince yourself, so it looks like v minus w doesn't go up or down at all. I'm going to pause the video, tell your neighbor why that makes sense numerically here. So one more time, so let's say I wanted to find a vector that's pointing in the same direction as v, so it's that vector, but whose total length is 2. I'm going to pause the video again and let you guys figure it out. First tell your neighbor, how long is v? How would you figure it out? And then how could you force it to be a length of 2 but still pointed in the same direction? All right, here we go. So the v vector is 5, 2. The magnitude of v is the Pythagorean theorem applied to this, so it's root 29. What if I want v to point in the same direction? So here's v. If I multiply v by any scalar, like what that literally does is it scales it. So it will either make it longer or shorter, but because you're applying the same scale factor to x and y, it's still pointing in the same direction no matter what scalar you use. So it's like I got to figure out what's a number that I could multiply my vector by so that when I apply the Pythagorean theorem, its total length is 2. So one thing you could do would be like set up an equation. Like let's say k times 5 comma 2 equals 5k and then 2k. And then I want like this to equal 2. So it would be like 5k squared plus 2k squared equals 2. And then you could solve for k. And like that would be okay. I think there's an easier way of thinking about this though. So here's a question for you. If the magnitude here is root 29, what would happen if I did this? What would happen if I scaled v by 1 over root 29? Tell your neighbors, what do you know about this vector? So a lot of people just said, the magnitude has to be 1. And hopefully it makes intuitive sense that that should be true. It's like, think about this as taking your vector and scaling it by dividing it by its own length. Like if you divide something by its own length, the length should end up just being 1 because anything divided by itself is 1. Okay, so if this is a length 1 vector, I've got an idea for how to make it a length 2 vector. Boom! Let's multiply it by 2. So, or you could think about it as 2 steps. Step 1 is divide the vector by its own length to become what's called a unit vector. And then step 2 is multiply the unit vector by the new length that you want it to be. So if you want to annotate this diagram here, so let's say divide by vector length to make it length 1, then multiply by new desired length. Here we go. So you can do algebra with vectors the same way you do algebra with numbers. So let's say I've got a plus b, and I want that to equal some third vector. First, let's just do it visually. So a is the vector 1, 5. So let's draw that. 1, 1, 2, 3, 4, 5. So here's the a vector. And then b, I don't know what it looks like, but I want it to end up being the vector 2, 1. So here's the vector 2, 1. So if a plus b equals 2, 1, it's like a, and then another vector b is going to have to be the same as this vector 2, 1. So just visually, I can see here that b needs to be over 1 down 4. So 1, negative 4. So I've just like visually solved for b, which, you know, is convenient because it was all small integers and it was all kind of easy to sketch. Algebraically, you can move these vectors around the same way as any other variable. So if I want to solve for b, let's isolate b by subtracting a from both sides. So I could rewrite this as b equals 2 comma 1 minus a. I know what a is. A is just 1 comma 5. And so I'll subtract component-wise. 2 minus 1 is 1. 1 minus 5 is negative 4, which is what we got kind of visually on this side. So I just wanted to point that out, that you can solve algebraic equations involving vectors the same way that you would anything else. Let's talk about basis vectors. So I don't know if you've seen this before. This is pronounced I hat. See how the I has a little hat? Distinct from what my daughter does. I heart. Yeah, it's a little joke for the video. Okay. So I hat is defined. Okay, joke over. I hat is defined as the unit vector 1, 0, which we could draw this way. So here's I hat. It's the vector that just points 1 unit to the right. J hat is the unit vector that points up. So here's J hat. It's pretty common to see other vectors written as a sum of a scaled I hat plus a scaled J hat. And hopefully this is going to be fairly intuitive when you see it. So if the v vector is over 1, 2, 3, 4, 5 and up 1, 2, so here's the v vector, I could imagine that same v vector as a vector that takes me right by 5 and added together with a vector that takes me up by 2. So what's a vector that takes me right by 5? It's just the I hat vector scaled by 5. Because if the I hat vector is length 1 and I scale it by 5, now it's length 5. And then if I add to that twice the j hat vector, the j hat vector points up, so twice that would take me up by 2. And remember, vector addition, it's like you do one vector and then you apply the other vector at the end of it. So if I do 5 I hat and then I do 2 j hat, that's the same thing as v. So it's pretty common to rewrite individual vectors by splitting up their xy components in terms of these simpler basis vectors. Notes concluded.